Our entire galaxy is a speck of dust in an unimaginably vast cathedral. We float in a universe not of random scatter, but of breathtaking architecture, woven on a scale that bends the mind. This journey will reveal 25 staggering facts about the largest structures in the cosmos, from walls of galaxies longer than time itself to voids of haunting emptiness. By the end, you will see the night sky not as a flat tapestry, but as a dynamic, three-dimensional map of colossal constructs that define reality itself. We will confront cosmic filaments that challenge the laws of physics and explore voids so large they create their own weather. What does it feel like to finally grasp your true, microscopic address in this grand design? This cosmic architecture has a name: the cosmic web. It is not just the largest structure in the universe. It is the fundamental blueprint of all reality we can see. Picture the universe not as a soup of scattered galaxies, but as a colossal, three-dimensional spiderweb spun across billions of light years. The thickest strands of this web are where galaxies gather in dense clusters and superclusters. These are connected by thinner, gossamer filaments of dark matter and intergalactic gas, forming a vast, interconnected network. And between these luminous threads lie the great cosmic voids, regions of staggering emptiness so vast they feel like separate universes of nothing. This entire tapestry, from the densest knot to the emptiest void, is the cosmic web. It is the large-scale structure of the observable universe itself, a single entity so immense it defines the very arena in which everything else exists. If you could step back far enough, our entire Milky Way galaxy would be just one tiny, glowing speck of dew, caught on a single silken thread in an infinite web. This cosmic web holds structures within it that defy our understanding of scale. Among its most famous threads is a contender for the single largest thing we have ever seen. It is called the Hercules-Corona Borealis Great Wall. Picture a filament, a single strand of this universal web, so long it would take light over 10 billion years to travel from one end to the other. To put that into perspective, the universe itself is only about 13.8 billion years old. This means a beam of light, the fastest thing in existence, would need to have begun its journey when the universe was still in its cosmic infancy to traverse this one structure today. Its discovery was as brilliant as it was indirect. Astronomers did not see it with optical telescopes. Instead, they mapped the locations of brief, cataclysmic explosions called gamma-ray bursts. These flashes are like cosmic lighthouses, signaling the locations of distant galaxies. When scientists plotted thousands of them, a shocking pattern emerged. An immense, dense concentration of galaxies formed a wall across the sky, spanning from the constellation Hercules to Corona Borealis. Its sheer size immediately sparked controversy. According to a fundamental principle of cosmology, the universe should look roughly the same in every direction on the very largest scales. A structure this immense, this lopsided, seems to challenge that idea. It appears too big to have formed given the age and known laws of the universe. Is it a true, connected structure, or a chance alignment of separate galaxy clusters? The debate continues, making this Great Wall not just a monument of scale, but a profound mystery that questions the very uniformity of our cosmos. The Hercules-Corona Borealis Great Wall may hold the record for scale, but another structure paved the way for its discovery. For years, the title of largest known thing belonged to the Sloan Great Wall. Mapped in the early 2000s by a pioneering project called the Sloan Digital Sky Survey, This colossal filament stretches for approximately 1.37 billion light years. That is a distance so vast. If you could stand at one end, you would be looking at light that left the other end before multicellular life existed on Earth. Unlike a solid barrier, this wall is a river of galaxies, a dense concentration of several superclusters all strung together along the same immense filament of the cosmic web. Its discovery was a watershed moment. For the first time, astronomers had a detailed, three-dimensional map of a structure so large it could not be explained by random chance. The Sloan Great Wall provided the first undeniable, large-scale proof that galaxies are not scattered randomly like stars in the night sky. They are organized, drawn together by gravity along these invisible threads of dark matter. It was the Sloan Great Wall that truly solidified our understanding of the cosmic web's filamentary nature, showing us that the universe builds on a framework of staggering proportions. It was the blueprint that made us look for even grander designs. But filaments and walls are not the only colossal patterns woven into the cosmic web. Sometimes, the brightest objects in the universe gather in ways that should be statistically impossible. Enter the quasar, a beacon of raw power. At the heart of a distant galaxy, a supermassive black hole feasts on surrounding gas. This violent process creates an accretion disk of incandescent material, glowing so fiercely it can outshine an entire galaxy of stars. This is a quasar, a lighthouse visible across the cosmos. And when astronomers began mapping them, they found something unsettling. 73 of these brilliant beacons appear to be linked, not just by chance, but as part of a single, immense structure. They called it the Huge Large Quasar Group, or Huge LQG. This cluster stretches an almost incomprehensible 4 billion light years across its longest dimension. To visualize that, if you placed one end at our Milky Way, the other end would extend far beyond our nearest galactic neighbor, Andromeda, and keep going for billions of light years more. Its discovery sent shockwaves through cosmology because of a simple, foundational rule called the cosmological principle. This principle states that on the very largest scales, the universe should look roughly the same in every direction. It should be homogeneous, like a well-mixed batter. There is a theoretical maximum size for structures, beyond which this smoothness should take over. The huge LQG is so vast, it appears to shatter that maximum size. It is a colossal, lopsided grouping in a cosmos that is supposed to be uniform. This sparked intense debate. Is this group a true, physically connected structure, or just a chance alignment of quasars at different distances, a trick of perspective? Does its existence mean we need to revise our models of the universe's large-scale structure, or our understanding of how quasars form? The huge LQG stands as a profound challenge, a question mark written in the light of 73 cosmic furnaces, asking us if the universe's blueprint might be even more complex and clumpy than we ever dared to believe. While quasars blaze with impossible light, other regions of space whisper in a different, colder language. This brings us to a shadow on the birth of the universe itself. The cosmic microwave background, or CMB, is the oldest light we can see, a faint afterglow from the Big Bang that fills the entire sky. It is our most precise baby picture of the cosmos, a nearly uniform sea of microwave radiation. But this picture is not perfectly smooth. It has tiny ripples, the seeds of all future structure. And then there is the cold spot. In the constellation Eridanus, there exists a region of the CMB that is significantly colder than the surrounding sky. This is not a small imperfection. It is a vast circular chill, a shadow so large and so statistically unlikely that it has puzzled astronomers for decades. What could cast such a cosmic shadow? One compelling theory points to a different kind of colossal structure, not an assembly of galaxies, but a profound absence of them. Astronomers have proposed the existence of the Eridanus supervoid. This would be an immense region of space, perhaps up to 1 billion light-years across, that contains far fewer galaxies, galaxy clusters, and matter than the cosmic average. It is a bubble of near emptiness on a staggering scale. The theory is elegant. As light from the CMB travels across the universe toward us, it gains or loses a tiny amount of energy depending on the gravitational landscape it passes through. Traveling through a dense cluster of galaxies, light must climb out of a deep gravitational well, losing energy and shifting slightly to the red or colder part of the spectrum. This is called the integrated Sachs-Wolf effect. But what if the opposite happened? If light traveled through a vast region of underdensity, a cosmic void, it would actually lose less energy than light traveling through an average part of space. Compared to the average, it would appear slightly colder. The Eridanus supervoid could, in theory, be that cosmic sinkhole, causing the light passing through it to emerge with a distinct chill, creating the cold spot we observe. Yet, here lies the heart of the debate. The void needed to create a cold spot this large and this cold would have to be unimaginably vast and profoundly empty. While surveys have found evidence of a large, underdense region in that part of the sky, many scientists argue it is not nearly large enough or empty enough to explain the anomaly. The numbers simply do not add up. This leaves a haunting possibility. If the void is not the cause, then what is? The cold spot could be a statistical fluke of such incredible rarity it should not exist in our observable universe. Or, more thrillingly, it could be a fingerprint of something beyond our standard model of physics, perhaps even evidence of a collision with another universe in the multiverse. The cold spot and its proposed supervoid represent a perfect cosmic detective story. We have a shadow, we have a suspect, but the evidence does not quite fit. It forces us to question whether we are looking at a known phenomenon pushed to its extreme, or the first glimpse of a reality far stranger than we ever imagined. This profound emptiness has a name and an address. To the ancient Greeks, Boötes was the herdsman, a constellation forever chasing the Great Bear across the northern sky. But within its borders lies a region that is the antithesis of a herd, a place of almost pure solitude. The Boötes Void is a spherical chasm of space, roughly 330 million light-years across. If you placed our Milky Way at its center, the nearest edge of this void would still be over 165 million light-years away in every direction. Within that staggering volume, a space that should naturally contain thousands of bright galaxies, astronomers have found only around 60. That is not just emptiness. It is a cosmic desert of unimaginable scale. Picture yourself on a planet inside one of those lonely galaxies. Your night sky would be a profound and permanent blackness. No nearby galaxies would be visible to the naked eye as fuzzy smudges. No Andromeda, no Magellanic clouds. The stellar neighbors you see would all be from your own isolated island galaxy, floating in an ocean of nothing so vast it defies human feeling. How could such a nothingness form? The leading theory is one of cosmic mergers. In the early universe, smaller voids naturally formed as matter clumped into filaments and walls. Over billions of years, these smaller bubbles of emptiness, like soap suds merging, could have drifted together and coalesced. Their boundaries touched, their interiors fused, creating one gigantic supervoid. This process is like watching raindrops on a windowpane slowly run together to form a single, clear channel. The Boötes Void is likely that final merged channel, a monument to the negative architecture of the cosmos. It earned its nickname, the Great Nothing, not because it is truly empty. It still contains dark matter and the faintest wisps of intergalactic gas, but because it represents the ultimate expression of absence in a universe we think of as full. It is a haunting reminder that the large-scale structure of reality is defined as much by what is missing as by what is present. Our place in the cosmic web is not a random speck of dust. For decades, we thought our galactic neighborhood was the Virgo Supercluster, a gathering of galaxy groups centered on the massive Virgo cluster. But recent, groundbreaking maps have revealed a humbling truth. The Virgo Supercluster is not a distinct structure at all. It is merely a dense limb, a bustling suburb of a far grander metropolis. Our true cosmic address is the Laniakea Supercluster. This Hawaiian name translates to immeasurable heaven, and it is a perfect description. Laniakea is a gravitational continent, a single, interconnected network of roughly 100,000 galaxies, spanning an incredible 520 million light-years. To visualize this, if our Milky Way were the size of a single house, the entire Laniakea Supercluster would be a continent larger than North America. But what defines Laniakea is not just a list of its members. It is defined by motion, by a shared destiny. Think of it as a cosmic watershed. Just as every raindrop in the Mississippi River Basin is destined to flow toward the Gulf of Mexico, every galaxy within Laniakea's borders is caught in a slow, relentless river of motion. They are all flowing toward a single, mysterious focal point of gravity known as the Great Attractor. This invisible heart of our supercluster lies hidden behind the dense plain of our own Milky Way, obscured by stars and dust. It is a gravitational anomaly so powerful, it is pulling hundreds of thousands of galaxies, including our own, toward it at millions of miles per hour. So, when you look up at the night sky, you are not looking out from a stationary platform. You are aboard a galaxy that is sailing on a river of space-time, part of a vast migration of 100,000 island universes, all drawn toward a hidden, powerful center we cannot even see. This redefines home. We do not just live in a galaxy, we live within the flow of a supercluster. This hidden destination, the Great Attractor, is one of the most profound mysteries in our cosmic backyard. It is a gravitational focal point, a place where the fabric of space-time itself seems to be tilted, pulling everything in our local universe toward it. Our galaxy, along with every other in the Laniakea Supercluster, is caught in this slow, irresistible current, moving at over 600 kilometers per second. Yet, we cannot see what is pulling us. The Great Attractor lies almost directly behind the crowded, dusty central plain of the Milky Way, in a region astronomers call the zone of avoidance. This is not a place of danger, but of simple obstruction. The thick clouds of gas, dust, and countless stars in our own galaxy's disk block our optical view completely, like trying to see a distant mountain through a dense, permanent fog. For decades, this region was a literal blind spot on our map of the cosmos. So, how do we know it is there at all? We feel its pull by meticulously mapping the motions of thousands of galaxies around us. Astronomers trace the river of their movement backward to a single, powerful source of gravity. It was like watching leaves floating on a stream and deducing the location of a massive waterfall downstream, even though a hill blocks our direct view. What could possibly exert such a pull? the leading theory points to a staggering concentration of mass. Behind the veil, surveys using radio and X-ray telescopes that can pierce the galactic dust have revealed a dense knot of galaxies known as the Norma Cluster. This cluster is immense, one of the most massive gatherings of galaxies we know, and it sits at the very heart of the Great Attractor region. But here is the catch. Even the combined gravity of all the visible galaxies in the Norma Cluster is not nearly enough to account for the tremendous pull we are experiencing. The math does not add up. This means the true engine of the Great Attractor must be something we cannot see directly. The prime suspect is an enormous halo of dark matter, that mysterious, invisible substance that makes up most of the mass in the universe. We believe this dark matter forms a vast, dense scaffold, a gravitational anchor upon which the visible galaxies of the Norma Cluster are merely the glittering decorations. So, the Great Attractor is likely not a single object, but a region, a gravitational basin where both visible and dark matter have pooled into a deep well in space-time. It remains one of the most tantalizing puzzles in modern astronomy, a powerful force that dictates our motion through the cosmos, yet one we must study indirectly by feeling its influence on everything around us. It is a constant reminder that the most important features of our universe are often hidden in plain sight, waiting for us to learn how to look. Yet the Great Attractor is not the only titan pulling on our cosmic neighborhood. From the opposite direction, an even greater gravitational force exerts its will. This is the Shapley Supercluster, the single most massive concentration of matter within 1 billion light-years of Earth. While the Great Attractor is a hidden basin of gravity, Shapley is a blazing mountain range of mass, impossible to miss. It contains not just dozens of individual galaxies, but dozens of entire galaxy clusters, each one a bustling city of thousands of galaxies. All of this is bound together into one staggering gravitational nexus. Its total mass is almost inconceivable, containing enough normal matter and dark matter to influence the motion of galaxies across an immense volume of space, including our own local group. Our journey through the cosmos is not a simple drift toward one destination. It is a cosmic tug of war. On one side, the hidden depths of the Great Attractor pull us inward toward the heart of Laniakea. On the other, the colossal mass of the Shapley Supercluster, located hundreds of millions of light-years away in the constellation Centaurus, pulls us in the opposite direction. Scientists measuring our peculiar motion through the universe have had to account for both of these colossal forces. The current understanding suggests that while the Great Attractor defines our local supercluster's flow, the Shapley Supercluster's immense gravity is actually the dominant influence on the larger-scale motion of our entire region of space. We are caught between two giants, one a shadowy vortex and the other a brilliant, overwhelming summit of light and mass. This competition of gravitational titans shapes the very path our galaxy has traveled for billions of years and will continue to follow for billions more. These titans pull on a framework far more delicate and intricate than themselves. If superclusters are the continents of the cosmos, then galaxy filaments are the mountain ranges and rivers that define them. These are the true threads of the cosmic tapestry, the dense, luminous highways of galaxies, gas, and dark matter that form the skeleton of the entire web. A single filament can stretch for hundreds of millions of light-years, yet be only 20 to 50 million light-years thick. Picture a strand of spider silk, impossibly long and slender, glistening with dew. In the cosmic web, each droplet of dew is an entire galaxy, and the silk is the invisible scaffold of dark matter that holds them all in a flowing line. These filaments do not exist in isolation. They are the cosmic connectors. At the points where multiple filaments intersect and tangle together, gravity wins its greatest victory, pulling matter into the densest knots in the universe, galaxy clusters. These clusters are the bustling metropolises, and the filaments are the superhighways feeding them with a constant flow of new material. One of the most stunning examples weaves its way through our own cosmic neighborhood. The Pisces-Cetus supercluster complex is not a single, dense cluster, but a long, winding filament of galaxies. It is a river of star systems so vast it contains dozens of smaller superclusters, including our own Laniakea, all strung along its meandering path like beads on an invisible string. This complex is one of the longest continuous structures we have identified, a primary artery in the web that demonstrates how even the grand superclusters we call home are merely components of something far more extended and elegant. To travel along a filament would be to witness a universe in a state of perpetual flow, with galaxies drifting slowly along these gravitational channels, destined either for a quiet journey along the thread or a final, dramatic plunge into the brilliant chaos of a cluster at its end. But these filaments do not drift forever in empty space. They converge, drawn together by gravity's relentless pull, to form the dense, brilliant nodes of the cosmic web. These are the galaxy clusters, the true metropolises of the universe. Imagine a single, gravitationally bound city containing not hundreds of stars, but hundreds of entire galaxies, each with billions of its own stars. This is not a loose gathering. It is a structure held in a violent, seething equilibrium. A classic example shines in the constellation Coma Berenices. The Coma cluster is a dense, almost perfect sphere of over 1,000 galaxies, all orbiting a common center of gravity. From within one of those galaxies, the night sky would be an overwhelming spectacle. Instead of a dark void punctuated by distant points of light, the heavens would blaze with the soft, fuzzy glows of neighboring galaxies, so close and so numerous they would crowd out the blackness of space itself. But the space between those brilliant galaxies is not empty. It is filled with the intracluster medium, a thin, superheated plasma. This gas is so incredibly hot, tens of millions of degrees, that it glows not in visible light, but in powerful X-rays. This seething ocean of particles is actually the dominant form of normal matter in a cluster, outweighing all the stars in all the galaxies combined. Yet, here lies the greatest mystery of these cosmic cities. Even when you add up the mass of every visible galaxy and every atom of that scorching intracluster gas, it is still not enough. The gravity required to hold such a fast-moving, massive structure together is far greater than the pull of all that visible material. Something invisible must provide the anchor. That something is dark matter. We believe each galaxy cluster is embedded within a vast, spherical halo of this mysterious substance, a ghostly scaffold that forms first. The visible galaxies and the hot gas are merely the luminous aftermath, falling into and being held by this immense, invisible gravitational well. So, a galaxy cluster is a universe in miniature, a dynamic balance of brilliant islands, a searing intergalactic sea, and an unseen, dominant force that binds it all into a single, titanic knot in the fabric of the web. This distinction between a city and a continent reveals a deeper truth about cosmic architecture. A galaxy cluster is a true, gravitationally bound structure. Its member galaxies are locked in a mutual dance, orbiting a common center, destined to remain together forever as an island in the expanding universe. But a supercluster is something entirely different. Our home, the Laniakea Supercluster, is not bound by its own gravity. It is a collection of these bound clusters and galaxy groups that are still flying apart from each other, carried by the overall expansion of space itself. Think of it as a vast archipelago of island cities, each city firmly held together, but the ocean between them is steadily growing wider. The galaxies within a single cluster are like buildings in a metropolis, connected by roads and bridges. The different clusters within Laniakea are like separate cities on different continents, all drifting on the same tectonic plate. They share a common motion, a local flow toward the Great Attractor, but they are not tied to one another. This is a crucial hierarchy in the universe's design. Gravity wins on the scale of galaxies and clusters, creating permanent structures, but on the scale of superclusters, the repulsive force of dark energy, which drives the universe's accelerating expansion, begins to win. This means Laniakea has no permanent future as a single entity. Over tens of billions of years, the space between its constituent clusters will stretch so much that the gentle gravitational tug they have on each other will be overcome. The shared flow will dissipate, and each cluster will become an isolated island, receding into the darkness. So when we map our supercluster, we are not mapping a permanent home, but a temporary confluence, a snapshot of a vast family of galaxies sharing a journey for a cosmic moment before the relentless expansion of space pulls them apart forever. The invisible scaffold of dark matter that shapes these clusters holds another secret, a ghostly echo from the very first moments of time. In the primordial universe, a mere 380,000 years after the Big Bang, the cosmos was not a silent void. It was a seething, opaque plasma, a dense soup of particles and light. In this hot medium, gravity tried to pull matter together, while the intense pressure of radiation pushed it apart. This created sound waves, literal ripples of compression and rarefaction that traveled outward through the infant universe. Then, in an instant, everything changed. The universe expanded and cooled enough for atoms to form, allowing light to travel freely for the first time. This moment of liberation, the release of the cosmic microwave background, also froze those sound waves in place. The ripples stopped propagating, leaving behind a permanent spherical imprint in the distribution of matter. These are the Baryan acoustic oscillations. Think of them as cosmic fossils, not of bones, but of sound. They created a preferred scale, a specific distance that became woven into the fabric of the cosmos. That distance is about 500 million light years. This means that when we look at the large-scale structure of the universe today, we do not see galaxies scattered at random intervals. There is a subtle, statistical tendency for galaxies to be separated by this specific scale, like the lingering rings from a stone dropped into a pond that has long since frozen solid. This fossilized echo is not a visible structure you can point a telescope at, but a statistical pattern etched across the entire sky. And for astronomers, this pattern is a gift of unimaginable value. It acts as a perfect standard ruler. Because we know the physical size of that original acoustic imprint from fundamental physics, we can use it to measure cosmic distances with incredible precision. By surveying millions of galaxies and measuring how this preferred separation appears at different distances, and thus different eras in cosmic history, we can map the expansion rate of the universe itself. We are using the ghost of primordial sound waves to chart the growth of the cosmic web across billions of years, turning an echo from creation into the most reliable measuring tape we have for the cosmos. That fossilized echo of sound is not the only pattern etched across deep time. In 2021, astronomers mapping distant galaxies stumbled upon a shape that should not exist. They named it the Giant Arc, stretching an almost incomprehensible 3.3 billion light-years across a region of the northern sky. This structure is not a dense wall, but a nearly symmetrical, crescent-shaped arrangement of galaxies, galaxy clusters, and intergalactic gas. Its scale is staggering. If you could see it in the night sky, it would span an area 20 times wider than the full moon. But its true significance lies not just in its size, but in its address. The giant arc exists at a redshift of about 0.8, meaning we are seeing it as it was when the universe was roughly half its current age. According to our standard models of cosmic evolution, the universe at that epoch should have been smoother, still in the process of forming the largest filaments and walls. A coherent structure of this immense scale simply should not have had enough time to assemble itself. It is like finding a fully formed, modern city in the geological record of the dinosaur age. The discovery directly challenges the cosmological principle, the foundational idea that on the largest scales, matter is evenly distributed. The giant arc suggests that the universe might be clumpier, with larger and more distinct features than our best theories allow. Of course, in science, one observation is a clue, not a verdict. The giant arc's existence is still being scrutinized. Is it a true, physically connected structure, or a chance alignment of separate galaxy clusters that just happen to form an arc from our particular viewpoint? Further observations and deeper surveys are needed for confirmation. But if it holds up, the giant arc becomes more than just another large thing. It becomes a profound question mark, a graceful curve drawn across the cosmos that asks us to reconsider the timeline and the very rules of how our universe built itself. The brilliant galaxies we see are merely the glittering lights on a far grander, invisible framework. Every filament, every wall, every supercluster is first sculpted by dark matter. This mysterious substance, which does not emit, absorb, or reflect light, interacts with the universe through gravity alone. And it is this gravity that creates the cosmic architecture we have been exploring. Dark matter forms immense spherical clouds called halos, which exist in a hierarchy of staggering scale. The smallest halos, with the mass of a dwarf galaxy, act as seeds. Larger halos, with the mass of a galaxy like our Milky Way, envelop those seeds. And the very largest halos, with the mass of entire galaxy clusters, contain all the smaller ones within their vast gravitational embrace. Think of it as a set of nested Russian dolls, but where each doll is an invisible sphere of ghostly matter. The ordinary matter we are made of, the protons, neutrons, and electrons that form stars and planets, is just a passenger in this dark universe. After the Big Bang, dark matter halos collapse first, creating deep gravitational wells in the fabric of space-time. Only then did clouds of ordinary hydrogen and helium gas, feeling that powerful pull, begin to flow inward. They cascaded down into these invisible basins, where they could finally cool, condense, and ignite into the first stars and galaxies. So every luminous galaxy we observe sits at the heart of a much larger, much more massive dark matter halo. The majestic Coma cluster is not held together by its 1,000 visible galaxies, but by a single, gargantuan dark matter halo that contains them all. The Great Attractor's immense pull is not from the Norma cluster alone, but from a titanic concentration of dark matter upon which that cluster sits. Even the delicate filaments of the cosmic web are at their core rivers of dark matter, with galaxies forming like beads of dew on the strands. Without this invisible scaffolding, the universe would be a formless, dim haze of gas, with no grand design, no walls, and no place for us to call home. The dark matter map is the true blueprint, and everything we see is just the illuminated decoration. This invisible blueprint forces us to ask a fundamental question about cosmic design. Is there an upper limit to how large a structure can become? In cosmology, this theoretical boundary has a profound name, the end of greatness. It is the scale at which the universe, when averaged out, should finally become smooth and featureless. According to our best models, this transition should happen at distances around 300 million light-years. Beyond that scale, the clumps and filaments of the cosmic web should blur into a uniform haze, like the texture of a canvas disappearing when you view the entire painting from far enough away. The universe should look roughly the same in every direction, a principle known as isotropy, the discovery of structures like the Hercules-Corona Borealis Great Wall, stretching over 10 billion light-years, directly challenges this elegant idea. If such a wall is a single, coherent structure, it exists on a scale where the cosmos should have no distinct features at all. It is like finding a single mountain range that spans an entire continent, when the map says the land should be flat prairie. This does not necessarily mean our models are wrong, but it forces a thrilling re-examination. Perhaps these colossal walls are not truly bound structures, but temporary alignments in the ever-shifting web. Or perhaps the end of greatness occurs on a far grander scale than we thought, meaning the universe retains its intricate architecture deeper into the void than we ever dreamed. Each new discovery of a giant arc or an immense void tests this boundary, probing the ultimate limits of cosmic construction and asking us where, or if, the tapestry finally ends and the smooth fabric of space truly begins. The blueprint for this entire cosmic architecture was not drawn by gravity alone. Its origin lies in an event of unimaginable speed and power in the universe's first fleeting moments. To understand why we have walls and voids instead of a perfectly smooth cosmos, we must travel back to a time before atoms, before light, before anything we would recognize as matter existed. This was the era of cosmic inflation. In the tiniest fraction of a second following the Big Bang, the universe is thought to have undergone a period of exponential, faster-than-light expansion. It ballooned from a subatomic speck to something roughly the size of a grapefruit in a span so brief it defies analogy. This was not an explosion into space, but a rapid stretching of space-time itself. And within that seething, energy-filled vacuum, quantum mechanics ruled. At the quantum scale, empty space is not truly empty. It is a frothing sea of virtual particles and energy, constantly fluctuating. These are quantum fluctuations, momentary flickers of something from nothing, governed by uncertainty. Normally, such fluctuations are vanishingly small and brief, appearing and disappearing in an instant. But inflation did something extraordinary. As space expanded at a staggering rate, it stretched these subatomic ripples in the fabric of reality along with it. The microscopic was blown up to the macroscopic. The tiny quantum whispers were frozen into the very geometry of the expanding universe, imprinted as minute differences in density, some regions ever so slightly denser, others ever so slightly more rarefied. When inflation ended, and the universe settled into the more sedate expansion we see today, it was left not as a smooth, featureless soup, but as a subtle patchwork of hills and valleys in density. These were the seeds. Over the next 13.8 billion years, gravity got to work. It acted as a cosmic amplifier. Those slightly denser patches had a tiny bit more gravitational pull. They began to attract more and more matter, both dark and ordinary, from the surrounding, slightly emptier regions. Over eons, the hills grew into mountains, and the valleys deepened into canyons. The densest seeds collapsed to form the first stars and galaxies. Those galaxies, pulled together by the underlying dark matter scaffold, lined up along the ridges of those ancient density waves, forming the filaments and walls. And the under-dense regions, drained of matter by their greedier neighbors, expanded into the vast cosmic voids. The Hercules-Corona Borealis Great Wall, the Boötes Void, the elegant flow of Laniakea, every colossal feature we have explored is fundamentally the grown-up, gravity-sculpted version of a quantum whisper from the first trillionth of a second of time. Our entire observable universe, with all its grandeur and emptiness, is the magnificent echo of a tremor in the newborn void. That quantum whisper left behind a universe defined by contrast. The brilliant filaments and clusters are only half the story. Their true scale and shape are sculpted by their opposite, the cosmic voids. These are not holes in the universe, but vast, three-dimensional regions of profound underdensity. To call them empty is a cosmic misconception. A void like Boötes is not a perfect vacuum. Within its staggering volume, you will still find a few isolated, lonely galaxies, often drifting like lost ships in a dark sea. You will find diffuse clouds of hydrogen gas, so thin they are 1,000,000 times less dense than the best vacuum we can create in a laboratory on Earth. And you will find dark matter woven into the same invisible filaments that structure the entire web, just stretched to an extreme thinness. A void is not an absence of structure, but a different kind of structure, one defined by what is missing. This emptiness is active, not passive. As the universe expands, the voids expand faster than the denser regions around them. Think of it like this. Picture a dense sponge representing the cosmic web. When you stretch the sponge, the holes within it grow larger at a faster rate than the solid material. This is exactly what happens on a cosmic scale. The voids are the stretching holes in the sponge of space. As they grow, their boundaries push outward. This expansion acts like a gentle, cosmic pressure, sweeping the sparse matter within the void toward its edges. This process is crucial. It is one of the primary engines that builds the dense walls and filaments. The matter evacuated from the voids piles up at their borders, feeding the growth of the surrounding web. So, the great walls of galaxies we marvel at are, in part, constructed by the outward push of the nothingness beside them. The void is the sculptor, its expansion carving and defining the luminous architecture we can see. Without these oceans of near emptiness, the cosmic web would be a faint, uniform haze. The voids create the contrast, the deep shadows that make the glittering threads of the tapestry stand out in breathtaking relief. This cosmic sandbox has a firm boundary, a horizon beyond which no telescope will ever see. All the titanic walls and voids we have discussed exist within a single, immense sphere called the observable universe. Its diameter is roughly 93 billion light-years. This is not the size of the entire universe, which may well be infinite. It is simply the portion of it from which light has had enough time to reach us since the Big Bang. Every photon, every radio wave, every signal of any kind that we can detect has traveled for no more than 13.8 billion years. But because space itself has been expanding during that light's journey, the most distant objects we see are now actually much farther away than 13.8 billion light-years. They are about 46 billion light-years away in every direction, creating an observable sphere with that 93 billion light-year diameter. This is our ultimate cosmic arena. It defines the absolute limit of our knowledge. We can map the cosmic web, hunt for great walls, and probe vast voids, but only within this sphere. Any structure larger than this observable universe, by definition, could not be fully contained within our field of view. Its light would not have had time to reach us from all its parts. So, when we declare something the largest known structure, like the Hercules-Corona Borealis Great Wall, we are making that claim only within the context of this finite, luminous bubble. There could be filaments, walls, or patterns of galaxies on scales that dwarf even our greatest discoveries, existing just beyond our cosmic horizon, forever hidden from our view. This makes the search for the largest structure a profoundly humbling endeavor. We are not mapping the universe. We are mapping our tiny, illuminated corner of it, forever wondering what magnificent architecture lies in the darkness beyond our sight. Our cosmic horizon is not a static border, but a shrinking window. The fate of every magnificent structure we have explored is already sealed by a force more powerful than gravity itself. Dark energy, the mysterious agent driving the universe's accelerating expansion, will ultimately dissolve the cosmic web. Picture the grand tapestry not as a permanent fresco, but as a drawing on the surface of an inflating balloon. As the balloon stretches faster and faster, the threads of the drawing are pulled taut, then begin to break apart. This is the destiny of our universe on the largest scales. First, the most delicate connections will snap. The gossamer filaments that link galaxy clusters, those rivers of dark matter and gas, will be stretched and severed. The superclusters, which are not gravitationally bound to begin with, will be the first to disintegrate. Laniakea will dissolve. The shared flow toward the great attractor will be overwhelmed as the space between its member clusters expands at an ever-increasing rate, carrying them apart like leaves on a raging river. Each galaxy cluster, however, is an island fortress held together by its own immense gravity. These metropolises, like the Coma cluster, will remain intact for eons. But they will become profoundly isolated. In the far, far future, the night sky from a planet in such a cluster will tell a terrifying story. All the galaxies within the cluster will still blaze nearby, but every other source of light beyond its borders will have disappeared. The rest of the universe will have been carried away by expansion so quickly that their light can no longer reach the cluster. The observable universe for that civilization will have shrunk to the boundaries of their own galactic city. Eventually, even the clusters themselves may face a more violent end. In some models, if dark energy's strength increases over time, it could lead to a big rip. In this scenario, the acceleration becomes so fierce that it overcomes all binding forces, not just between clusters, but within them. Galaxies would be torn from their clusters, then stars ripped from galaxies, and finally planets and atoms themselves shredded apart. While this is a more speculative extreme, the core principle is certain. The architecture of the cosmos is temporary. The walls, the filaments, the vast basins of gravity, all are structures in a river that is flowing faster and faster, destined to be pulled apart into isolated fragments, then into nothingness. The largest structures will not be conquered by time, but unraveled by the very fabric of space. Before the Hercules-Corona Borealis or the Sloan Great Wall, there was a discovery that fundamentally rewrote our map of the cosmos. In 1989, a team of astronomers from the Harvard-Smithsonian Center for Astrophysics, or CFA, published a stunning three-dimensional map of the nearby universe. For the first time, they saw it, a colossal, dense sheet of galaxies stretching across the constellation Coma Berenices. This was the CFA2 Great Wall, often called the Coma Wall. It was a monumental ribbon of light, over 500 million light-years long, 200 million light-years wide, but only about 15 million light-years thick. That is a structure so immense it would take a beam of light 500 million years to travel its length. Yet it is as proportionally thin as a single sheet of paper stretched across a continent. Its discovery was a seismic shift in human understanding. Up until that point, while we knew galaxies gathered in groups and clusters, the prevailing assumption was that on the very largest scales, the universe was essentially a smooth, random scatter of islands. The CFA2 Great Wall shattered that notion. Here was undeniable visual proof that galaxies organized themselves into coherent structures of almost unimaginable scale. It was not a random cluster, it was a vast architectural feature, a true wall in the fabric of space. This single observation provided the first concrete evidence for the filamentary nature of the cosmic web, transforming our view from a universe of isolated points to one of grand, interconnected design. The Coma Wall was the first glimpse of the universe's true skeleton, a revelation that every giant structure found since stands upon the shoulders of. That first glimpse of cosmic architecture set the stage for discoveries far more ancient. In 2017, astronomers in India unveiled a supercluster that redefined what we thought possible in the early universe. They named it Saraswati after the Sanskrit word for a celestial river, a name that perfectly captures its nature as a vast flow of galaxies within the cosmic web. But Saraswati is not just another supercluster. It is a fossil from a time when the cosmos was in its adolescence, a colossus that should not exist. Located an astonishing 4 billion light-years away, we are seeing it as it was when the universe was only about 10 billion years old. At that epoch, according to our best models of cosmic evolution, matter had not yet had enough time to gather into structures of such staggering scale and mass. Gravity works slowly, pulling galaxies together over billions of years. Saraswati, however, appears fully formed, a titan that assembled with a speed that defies expectation. It contains the mass of at least 43 massive galaxy clusters, a gravitational continent of perhaps 20 quadrillion suns. To find a structure of this immensity so far back in time is like discovering the ruins of a modern skyscraper in a geological layer from the age of the dinosaurs. Its existence forces cosmologists to ask difficult questions. Did we underestimate the initial clumpiness of matter after the Big Bang? Are there unknown mechanisms that accelerated the growth of these cosmic behemoths? Or does Saraswati hint that dark energy, which now drives expansion, behaved differently in the ancient universe, allowing gravity to work faster and build these colossal islands sooner? Saraswati is more than a distant landmark. It is a profound challenge, a river of galaxies flowing from the past, asking us to reconsider the entire timeline of cosmic construction. These colossal structures remain invisible to any single telescope. To see them, we must step beyond flat pictures of the night sky and learn to map in 3 dimensions. The key lies not just in where a galaxy is on the sky, but how far away it is. Astronomers unlock this 3rd dimension using a cosmic fingerprint called redshift. As the universe expands, it stretches the light from distant galaxies, shifting it toward the red end of the spectrum. The greater the redshift, the farther away the galaxy, and the further back in time we are looking. By pointing powerful telescopes at vast swaths of sky and measuring the redshift of millions of individual galaxies, we can plot their positions in a 3-dimensional volume of space. This is the science of redshift surveys, and they are the engines of our cosmic cartography. Pioneering projects like the 2-degree field galaxy redshift survey, or 2DF, in the late 1990s, mapped over 200,000 galaxies, providing the first detailed, large-scale view of the Webb's filamentary structure. But the true revolution came with the Sloan Digital Sky Survey. Starting in 2000, this ambitious project used a dedicated telescope with a camera containing over 100 million pixels to systematically image and measure redshifts for more than 3 million celestial objects. The Sloan data did not just give us points on a graph. It allowed scientists to create the first breathtaking, 3-dimensional visualizations of the cosmic web. You have likely seen these fly-through videos, where the camera seems to plunge through a universe of glowing filaments and dense clusters. Those are not artistic interpretations. They are direct visualizations of the Sloan data, a point-by-point rendering of millions of measured galaxies, revealing the grand architecture in which we are embedded. Today, this work is being pushed to new frontiers by the Dark Energy Spectroscopic Instrument, or DESI. Mounted on a telescope in Arizona, DESI can capture the spectra, and thus the redshifts of 5 billion galaxies at a time. Its goal is to create the largest 3-dimensional map ever made, cataloging tens of millions of galaxies and quasars. Each new survey is like turning on a brighter light in a vast, dark cathedral, revealing finer details of the pillars and arches we once only guessed were there. These maps are more than just pretty pictures. They are the data sets that allow us to measure the Great Walls, trace the boundaries of voids, and ultimately decode the history and fate of the universe itself. The true scale of these structures defies every earthly comparison we possess. To even begin to grasp it, we must shrink our own home to an almost invisible speck. Picture our entire solar system, from the sun to the distant Oort cloud, compressed into a single grain of sand. On that scale, the Milky Way galaxy, our island home of hundreds of billions of stars, would be roughly the size of North America. That entire continent of stars is our local neighborhood. Now, hold that continent in your mind. The Hercules-Corona Borealis Great Wall, that single filament of the cosmic web, would be a structure larger than the entire surface of the Earth. Our galactic continent becomes a mere town lost in a planetary-scale landscape. This is not an exaggeration. It is the mathematical reality of the cosmic hierarchy. If we go smaller still, the analogy becomes even more staggering. If our Milky Way galaxy were the size of a standard coin, a quarter resting in your palm, then the span of the Hercules Great Wall would be wider than the continent of Asia. Every star, every planet, every potential civilization within our galaxy is represented by the microscopic metallic ridges on that single coin. And it is utterly insignificant against the backdrop of this one architectural feature. These are not just big things. They are the canvas upon which big things are painted. They are the mountain ranges of reality, and our most majestic galaxies are merely the dust that has settled on their slopes. To understand the universe is to accept a profound and beautiful insignificance, to see that our entire local universe is structured on a framework so grand that our home galaxy is not even a notable landmark, but a speck of pollen adrift in a continental wind. Yet all this cosmic architecture is far more than a gallery of superlatives. These titanic walls and voids are not just passive monuments, they are active cosmic laboratories. Each filament, each supercluster, each sprawling void is a grand experiment in physics, running on a scale and across a time frame we could never replicate. By observing how these structures form, evolve, and interact, we are conducting fundamental tests of the universe's most profound laws. Their distribution across the sky is a direct imprint of the universe's ingredients. The precise spacing between galaxy clusters, the subtle statistical echo of baryon acoustic oscillations, tells us exactly how much ordinary matter, and dark energy make up our cosmos. The growth of these structures over billions of years, from the smooth early universe seen in the cosmic microwave background to the intricate web we see today, acts as a stopwatch for gravity. It shows us how quickly matter clumped together under its own pull, and that rate of growth is now in a cosmic tug-of-war. Gravity wants to pull everything together to build ever larger and denser structures. But dark energy, driving the accelerating expansion of space, is working to pull them apart. By measuring the largest structures at different distances, and thus different eras, we can see which force is winning and how the battle has changed over cosmic history. The Saraswati Supercluster, so massive so early, may be a clue that dark energy's influence was weaker in the past, allowing gravity to build giants faster. The potential dissolution of superclusters like Laniakea in the far future is a direct prediction of dark energy's ultimate victory. So, these colossal features are not just scenery. They are the diagnostic charts of the universe's health, the grandest clues we have to its composition, its past, and its ultimate fate. They allow us to weigh the invisible, to clock the expansion of space, and to trace the story of reality from a quantum whisper to a web of light. In the end, mapping the largest structures is how we read the autobiography of the cosmos itself, written in galaxies and etched across the void. From the delicate filaments of dark matter to the sprawling continents of superclusters, this journey has revealed a universe of breathtaking architecture. We have traced the gravity rivers that define our home in Laniakea, felt the pull of invisible titans like the Great Attractor, and stood at the edge of voids so vast they sculpt the web itself. Each fact is a testament to a cosmos structured on a scale that permanently recalibrates our sense of place. Our entire galaxy, with its hundreds of billions of stars, is a fleeting spark on a single thread of an infinite tapestry, a tapestry woven from quantum whispers in the first instant of time. To grasp this is to embrace a profound and beautiful humility. We are not at the center of anything, but we are witnesses to everything, capable of mapping the very walls of our celestial cathedral. This perspective is not meant to diminish us, but to liberate our curiosity. So, the next time you look up at the night sky, remember you are not looking at a flat canopy of dots. You are gazing into a dynamic, three-dimensional labyrinth of light and shadow, of colossal walls and profound emptiness, a realm where the largest things imaginable are still under construction. Which of these 25 facts reshaped your view of the cosmos the most? Let us know in the comments below. If this journey through the largest structures left you in awe, be sure to like and subscribe for more explorations into the mysteries of space. Thank you for watching.